Welcome everybody, exciting to see so many people attending the webinar. Today's title is Kubeflow, MLFlow and Beyond, Augmenting Machine Learning Delivery. I'll be focusing more on Kubeflow. It doesn't mean that Kubeflow is better than MLFlow. I'm just trying to show them some options, and we have limited time, so I'll be more than happy to follow up later on any questions. Yeah, clicking next. So agenda, start with mutual introductions to get to know each other. Then we talk a bit about the why aspect of this topic in general, why we need yet another flow engine, workflow engine, why it's not sufficient to have existing tools in the ecosystem. Then we'll do a really quick Kubeflow overview from the very basis to some advanced concepts. Hydrosphere, so I present here a Hydrosphere IO project and the company. So a brief introduction of this company and tool set as well. Then practice. So we'll be defining and implementing worker containers that will enforce us to build our main Kubeflow pipeline. Then run train. Sorry, there's a misprint here. Test and deploy a machine learning pipeline with Kubeflow, and then simulate production traffic to see the kind of simulate a real-world use case with some outliers, with inliers, and so on. And then we'll do a monitoring and of data and domain drift. So the timeline-wise, I'm going to spend about 20 minutes on slides and 20 minutes on practice and 10 minutes on questions. So bear with me through the slides, and we'll switch quickly to the practice mode. Yeah, brief introduction about myself and why I'm here and why I'm talking this topic. So back to 2016, I published a blog post on KD Nuggets. That topic was big data science expectations versus reality. And I was talking those days about lack of tooling in that ecosystem, machine learning ecosystem specifically, and the path from research to production is not as simple as it might seem to be. And there were a few takeaways I had in my blog post. The first one is tools evolution. So we needed more tools, and we see right now it's happening. A lot of cool, exciting projects that augment machine learning ecosystem, and you've probably most of us have seen the research from Google about the hidden gap in machine learning, and like 99% of the machine learning is not actually machine learning itself, and not an algorithms, but all that support those algorithms to work reliably and consistently. Then education and cross skills. So the notion of data scientists who used to work in some silos in universities, and they need to get cross-trained with engineers, and engineers will need to do some to take courses in the machine learning basics. So to speak the same language, use the similar methods, and basically deliver applications to production, because all the applications nowadays become machine learning applications. So at least they have some underlying machine learning brain behind it. And the process, the third takeaway was the process, improving the process, and with DevOps-like mindset, that with continuous delivery, continuous integration, that we we've been doing for a while in the classical software engineering world, and that was the idea that we need something similar. So it was back to 2016, and at that time I had hard time explaining this to people. To people. Right now, kind of the maturity of the ecosystem, maturity of the community and industry is evolved. So we can right now speak the same language and talk about all the exciting things that happening in the world. So and since that time, we got some traction as Hydrosphere.io project, and we got a couple of exciting like production integrations, some customers. So we are happy to be kind of a facilitator and one of the key players in this community. So why so? Back to 5 years ago, there was a machine learning, and machine learning looked like this. So we had a business problem, we had data, and enterprises were to hire a data scientist, put him in a black box, and express high hopes about the final outcome. So we dreamed about the machine learning and how well we can live in the future. So, and then after a few years, somebody opened that black box, and what we see there, what he discovered, hey, there is a lot of Python. There's a lot of, like so much Python code, thousands and thousands of lines of that Python code, and we still have high hopes that this Python code will work reliably in production. But it's not the case, unfortunately, and people tend to apply their engineering mindset, apply their like programming skills to decouple things. And as a community, we started whitening that black box and modularizing what's there. So we're outlining a machine learning workflow or machine learning life cycle. So this is a very rough idea how it may look like. Most of you might be very familiar with that, but I will repeat it for the to put it on the same context. So we start with research, we start with data preparation, then we do model training. Once the training is done, we need to put model somewhere to repository or to catalog for further discoverability and versioning. Once the model is there, we need to deploy it to production, and to production or to some environment. We need to perform some testing, integration testing. It differs from the model testing in a training cycle. So we test it end to end with some edge cases, with some golden data sets, and apply kind of business acceptance criteria before pushing it finally to production. Production inferencing is not a step; it's kind of it's a process. So it's continuously happening in production, of course. And so another continuous step is monitoring. So as traffic goes, as traffic inferences our model, we need to constantly monitor, not only a latency and some system metrics and CPU and memory, etc. But rather than model quality, it's accuracy that is being changed over time, and another interesting aspects like domain drift or data drift. And model maintenance goes the next. It's one of the crucial component of the whole life cycle. So of course, like the real example might be much more simpler and much more complicated depending on the use case. And each of those steps that outlined here may have many other sub-steps. But to give you an idea how in general it could look like. And the fundamental concept I would like to encourage you to think about this whole workflow. So we need to imagine it as a pure function that takes the immutable raw data set, applies a particular function, and as an output of this function, we have a machine learning service working in production. So if that function is really pure, we will be having the same output each time we will run this function if with a given input. So it's kind of fundamental thing that if we will be designing our pipelines this way, we will have a repeatable, scalable, observable machine learning operations. So switching to the tool set. So today's topic is one of the keywords from today's webinar is Kubeflow. I believe most of the audience already visited kubeflow.org landing page, read through the docs, maybe watched some videos. But I will remind what Kubeflow is in a nutshell. So it began as a Kubernetes template and a blueprint for running TensorFlow on Kubernetes. For the first, I guess, year after Kubeflow has emerged, there was nothing rather than just tutorials and some template Kubernetes configs, how to set it up and run. So it was more like educational project with a big idea in mind. So and it eventually evolved into toolkit by basically loosely coupled tools and blueprints for machine learning on Kubernetes. Still not clear enough, especially. So, how can I kind of what's the tangible aspect of this toolkit? Because we see like TensorFlow, Jupyter, Khatib, Argo, TensorTip, and other like logos here are basically just independent projects. And what is basically an original contribution of the Kubeflow team? And I was wondering about that myself until Kubeflow Pipelines has been released. So Kubeflow Pipelines is basically the very first original contribution of Kubeflow team. What it does, what it has. You can think about this as a extension on top of Argo. Argo is a Kubernetes native Git flow engine. In a simpler words, it's a continuous delivery for Kubernetes native applications built also on Kubernetes. And the Kubeflow pipelines is a nice abstraction on top of Argo configs that allows us to use Python SDK and nice UI to build machine learning pipelines. Basically, any pipelines, any continuous delivery pipelines. But as far as the project is focused on machine learning, we will be discussing what's the machine learning aspect of this. And the first component, which is listed here, is a metadata service. The metadata service is basically designed to capture all the metadata that is being produced during machine learning pipeline. Quick architecture also from the kubeflow.org. Some of you have like explored that already, but very quickly some microservices architecture, different components. Some of them are kind of just pure infrastructure components, how to run tasks on Kubernetes, how to manage that Kubernetes controller. The key aspect, one of the key aspects that I'm paying attention to is machine learning metadata service. It's basically what makes the difference from the very general CI/CD pipeline, CI/CD tool is the ability to capture those metadata and interpret and visualize this metadata in the right way. The rest of the components are kind of reinvented. The wheel which is reinvented on the purpose with the purpose of Kubeflow, like artifacts, store, some UI components, pipeline builder, pod controller. So the nice things that are in a roadmap here is like data-driven workflow controller. Basically, it's not just a task-driven, but also a data-driven. So once data arrives, so we can trigger some steps in our workflow, and many others. In short, Kubeflow pipelines bring machine learning awareness into the continuous delivery. As I mentioned, metadata is a key aspect that I'm paying attention to. So Kubernetes native enforcements of Docker-only pipelines. That's kind of I want to like stop here and just spend time on this. So there are many ways of writing pipelines. You can just build like arbitrary Python code, split it into modules, and call each module one after another, kind of from your main script. So, but here Kubernetes native means that each step of your pipeline is just Docker, is a separate Docker container with arguments and outputs. So there is literally no other way of just killing yourself by calling an arbitrary Python script from somewhere in your pipeline. And this is particularly what I like about this. Yeah, we will see it in action in a couple of minutes. Just strong belief in Kubernetes community. Here is some like some bias. Not saying it's the best, but if you really hear, it's kind of the aspect. Some concerns, still low level, and basically to have it up and running, you still need the ops team, especially if you're a data scientist. It's kind of there is no local mode. You will need to install Kubernetes Minikube. They're still working on some local mode. The local mode is on the roadmap. In terms of like running Docker containers and passing parameters there and reading in outputs is kind of not a big deal, but having a DSL on top of that might be very helpful. So there's no still it's kind of very general framework. Little to zero machine learning abstractions, machine learning adapters, but it's coming from the roadmap. That's why I mentioned here strong belief in Kubernetes community. If you believe community will deliver, and if you believe and you want to contribute there, so it's kind of the way to go. A bit religious here, but let's quickly talk about alternatives. So of course, like ops guys who used to run Jenkins and GitLab pipelines for a while would say, hey, this is the same. We are reinventing the wheel, and we can close the gap with machine learning plugins. Yes, they might be right, but those machine learning plugins do not exist yet, to the best of my knowledge, and somebody needs to write it. That's kind of, and somebody needs to focus on this. So it's just a broad focus versus very narrow focus of Kubeflow. So Airflow, another like broader focus engine running workflow like workloads. So there is a Docker operator in Airflow, and like adding more specifics or more domain specific, adding more like machine learning operators like training operator, evaluation operator, testing operator, may close the gap if community is really focused on that. So it's just a matter of looking at the roadmap and the main drivers for this community. Other commercial workflows like workflow engines as AWS step functions. In a nutshell, it's also the way to describe your pipeline. And but all the integrations with TensorBoard, all the integrations with some machine learning specific visualizations need to be done by yourself. So MLFlow is another alternative, and it's not even an alternative. I will show in a couple of minutes how we can combine the best of both tools, Kubeflow and MLFlow. But there is a big overlap with functionality and vision where they want to be. So simpler architecture, I would say. Not so heavy microservices. Microservices and basically it's so a big monolith, like a JS and Python monolith. Easier to start. There is local mode of running your pipelines, and experiments tracking is better, meaning that it's just it was on top of their pipe roadmap, and this is the first thing they did, and it looks it really works well, rather than like Kubeflow is just lacks of this this functionality, and they do have gather all the metadata, but currently there is no user-friendly interface for comparing experiments and so on. Could be run on Kubernetes, but not as native as Kubeflow, especially in the community. So just different community, Databricks, Azure. Also, some of you who are kind of religious, you can just follow this different communities just because you believe them. So very quickly, what's a hydrosphere? We categorize as platform for machine learning models management. So we started as an open source microservices native machine learning serving. Just when TF serving, when other tools didn't exist. There are many serving projects nowadays, but back like a few years ago, we were alone. So we kind of position in this in the context of this webinar, we position ourselves as an exact value add tool that could be hooked into Kubeflow pipeline and could be part of this Kubeflow toolkit. And we cover model cataloging, deployment, inferencing, monitoring, and maintenance steps. So we can use them as an API to trigger it from the Kubeflow pipelines. A brief architecture also like very microservice oriented. There is as an input from the user, we expect some model binaries and some configuration serving YAML. And like kind of, and then like we do all the magic under the hood and provide HTTP and gRPC or Kafka API for the client applications, so you can integrate your machine learning models into end-to-end enterprise architecture. And there are things that we really focus on is these components of Sonar and request store here. We do a concept drift detection, edge case detection, accuracy monitoring, some A/B canary monitoring loop, and data profiling. So we will see it in action in a couple of minutes. So today's tools landscape, the same this pipeline and the logos underneath. And we will be really focusing on this like Kubeflow pipelines that will orchestrate all that stuff. So for the code, follow this link on GitHub hydrosphere data/workshop. There is a brief README there. You can even run it yourself in case of any issue. Just let us know. There is Gitter chat, so you can basically get some get our hand there. So the switching to practice. Well, on the first part, we will implement that forward path from data preparation, model training, model releasing, deploying to prod, integration testing, and deploying to production, that pipeline. Then we will simulate production workload. So basically send some traffic and see how our model behaves in production. So some like accuracy, watch some accuracy metrics, performance metrics, and trace predictions. Some like edge abnormal predictions or even normal predictions, basically show the observability of our production system in action. And we will, as like the last step, we will close the loop between training and retraining. So once we will see the model is to be degraded in production, we'll run retraining and with the latest data set from production, and we'll see how our metrics will become green again. So the sustainability and reliability of that machine learning model in production will be in action. I'm switching to practice mode very quickly. Let me show you, for those who is not familiar with Kubeflow UI, the main concepts here. Pipelines are basically your templates, just your descriptions of the argue descriptions of your pipeline. So you can define this pipeline. This is very simple, one-step pipeline like this. So you define steps here. They are all connected using input and output parameters. You even may not specify explicitly what step you need to run, and basically Kubeflow pipelines, they automatically connect your steps depending on the arguments required for a particular step to get executed. So under the hood, there is, as I mentioned, Argo. So this is what you've seen. It's a visualization of Argo YAML file. Obviously, it's not so user-friendly to develop and basically implement this huge Argo file. That's why the Kubeflow pipeline DSL has been invented here. And experiments are basically just grouping of pipeline runs, the same notion as in MLFlow and other data science collaboration and experimentation tools. So we have experiments and experiment runs. So each run uses a pipeline as a template to basically execute this run. As I mentioned, switching to the code editor. What we have here in our setup have steps. Each step is basically a Docker container, a Docker image with some logic, a task or a microservice that does a particular small thing. For instance, deploy, download, like test, train model, and so on and so forth. So it kind of enforces your structure of being like microservices driven. You cannot write just arbitrary Python scripts here. Each step has a simple Docker file, and in our case, it's just a Python implementation of this step. In the early stage, there is a pending feature in Kubeflow pipelines for avoiding this boilerplate Docker definition files, basically converting arbitrary Python functions into Docker files, but it's not the and it's out of the scope of this webinar. So there are the steps, and there is a workflow itself. So let me start with writing. I will just to simplify this, I will write a simple one-step workflow just to show you a DSL, and then we'll switch to the end-to-end whole-blown pipeline. So, for instance, if I let me explain. So it's a KFP importing that Kubeflow pipeline DSL, and we importing that kind of GCP secret secret interface. So there's the DSL itself. You basically annotate the method with DSL.pipeline and name your pipeline with however you want. And you define steps. For instance, download is DSL.container up. This is the only one DSL you need to learn to get started with the Kubeflow pipelines. And basically, you specify name, download. You specify image, basically Docker image that is being used to run this pipeline. So it's like this. Manist pipeline download. So we specify the tag here. Then you specify arguments. Arguments here is a bucket name. Bucket name, the name of bucket the data needs to be downloaded into. We will specify it in a minute. And the outputs are basically what you expect from this step to get into output. So we expect this data path from data path txt. So that's kind of not quite convenient. Not quite convenient way of passing parameters in and getting parameters out, but getting an output out. But this is what it is, and you basically tell apply and use GCP secret. So that's it. You kind of define your step. You basically need to take a look closer what and debug further what's required for your step. But this is the main DSL and quite easy to learn, quite easy to get started. For the data under the hood, data path is a TXT file which is being saved by the this particular image Docker container, and it's kind of the way and convention and the way of Kubeflow exchange parameters and outputs between different stages and get those stages are being orchestrated this way. Yep, and for this, let me just just to ensure I haven't I typed everything correctly. I will copy and paste. Oops. Yep. Copy and paste it from the already developed pipeline. Here I'll just hardcode latest. The bucket name. Let me just hardcode it here for a second. Yep. So here we go. We can compile this this pipeline. As an output, we have a pipeline tar gz, and this is the basically something that needs to be uploaded into Kubeflow. Kubeflow, there is a command line interface, so you can, or an API, you can send it from the command line, but just because of some there's authentication here, which is not that doesn't work through the API. We will just go and manually upload this. So we specify a file. We specify it here. Yeah, open. Oops, what's going on? Let's try one more time. Yeah, it's here. My first pipeline. So your first pipeline, you see we specify this single download step. It accepts the arguments and uses an image, and it outputs the download data path here. So you can create a run from this run basically. So I will switch to the kind of the whole blown like end-to-end pipeline, just demonstrating you the core concepts of this. So if we switch back to this to our main pipeline, let's see what's there. So basically, there are steps, definitions, container, all the same DSL, download, train model, train drift detector, a separate model that will watch the main one for some data for the data quality purposes. We are releasing releasing drift detector, releasing main model, main MNIST model, deploying to stage. We will use a staging environment, staging namespace to test our models for end-to-end and apply some like golden data sets and basically regression, run a regression through this model. Yeah, it's defined in a test in a testing step. So as a testing step, you see, yep. For then, once the testing is passed, we deploy the model to production, also as a DSL container operations, and passing all the metadata that we captured during the training pipeline into this into the latest step here. Also, I have uploaded this, compiled and uploaded this pipelines already before, so not to waste the time right now. We can create a run. So this one, the pipeline itself, it looks like this. Nice visualization. The second, origin. Yep. Here we go. So we can create run out of it. Let's see, ODSC run, ODSC run, and experiments. We'll group our run into show real experiment. So let's get started. Keep fingers crossed. So it's being launched in the cluster. It takes us probably like 2 minutes to pass through while it's running. So yeah, you see it's while it's running. Let me show you quickly from the train model. Train model uses a very familiar to everybody, the like MNIST estimator. What's there? Like Kubeflow specifics. So we output the metrics in this format, and we output the metadata also in the format of just a JSON format. And in this case in CSV format. And this is specifically just to tell there is a convention that Kubeflow will just hook into this outputs and visualize it as an output of this particular step on a Kubeflow UI. So this is a convention you should follow in order to get integrated with the machine learning kind of visualization plugins there. And also what we do here. 1 second. Yeah. We on the side we log this data, we log this runs and the experiments into MLFlow. So basically the same metadata goes to both Kubeflow and MLFlow, but the pipeline itself is being run from the Kubeflow. So and we will see how they differ in a second. Let's see what's there. Just deploying our stuff. Yeah, train the model. Here you see the output. The output that I have, those metrics that it's basically a confusion matrix, but we use just a table representation of this confusion matrix. There is a separate confusion matrix kind of plugin and component in Kubeflow, but unfortunately it doesn't work it doesn't work on multi-class use case. By some reason, it just works on a binary use case. I believe it's panning, so there are some panning work. So in TensorBoard, we can take a look at the TensorBoard. There is some integration, nice integration here. We can get started right from here, and yeah, let's see. It's starting while the pipeline is progressing further. Yeah, pop it out. Let me update and see. Hey, where's that? On the ODSC run, train the model. Yeah, there's a TensorBoard launched. You can basically see what it's a well familiar TensorBoard, but the nice thing that yes, there is. What's the difference between the general CI/CD pipeline? Yeah, there is an integration. The integration could be done like manually with any other Jenkins-like setup, but this is like out of the box setup. For the next steps here, so just testing is in progress. So the model is deployed. In this case, when we release the model, we use Hydrosphere SDK to basically store the final artifact in Hydrosphere cluster here. So there you see this URL. Let me go there. That UI and see. So 3 minutes ago, there is a model, version 16. The versioning is happening like automatically here. There is some metadata captured from the training pipeline that just encourage you to gather everything that you have in your training pipeline, so you will have this immutable package of something that is deployed in production. So you will be able to track it back, what metadata, what data, for instance, what test training data has been used for this model to train with, what hyperparameters were used to train this model, and other like user-defined metrics, metadata that you want to be captured. There's also other metadata about like inputs and outputs of the model. It's basically a signature, TensorFlow signature that is being extracted automatically. And yeah, you can see logs here. It's just the Docker logs when you upload the model, the Docker image is being built and pushed to the Docker registry. So let's see. We have a pipeline finished. So the model has been deployed to staging and then tested. Basically bombarded with some data set, and the accuracy has been let's see, test the model. Let's see what the input parameters. Yeah. And we basically follow the forward path of this pipeline and have this model basically deployed in production. Currently, there is an instance of this model running in production. I would like to use the notebook and simulate a production workload. So let me just start this. This is just a separate notebook I used just to send HTTP requests with MNIST dataset. And the tricky thing here is I'm not sending just the MNIST digits. I'm sending some like combined here, just letters and digits. So all of a sudden, so we've trained the model on a classical canonical MNIST dataset, but all of a sudden in production, we can observe all the time some domain drift. Somebody starts sending a bit different inputs, or just we basically discovering edge cases for our model in production. So let's see what's going on there. We go to monitoring. And the accuracy. So this is a leaf console here. We see a drip detector is being alarmed. We also can see the requests. So those are requests, new requests that are being like sent to the model, and the accuracy drops from the almost like 95% here. It drops dramatically just because we can zoom in into like a recent data set, and we see we can observe some like strange inputs like letters here, and make it like a conclusion out of it that probably the model needs to be retrained, or those letters probably needs to be filtered out from the output, because from the input, because it might be some like adversarial input or something that we really do not expect our model to handle. However, if the model is basically needs to handle the letter, recognize both the digits and letters, we can use this kind of production data sets to subsample it the next retraining batch and run this. So I have another retraining batch here, retraining pipeline, and where is that? Yeah, this one. So instead of just downloading a canonical MNIST dataset, it subsamples from production. It basically uses Hydrosphere API to give me the most relevant dataset, the most kind of the dataset with the right distribution from production, and run it through. So we like retrain run. We'll launch this retrain run. We would like to group it into the same experiment. Let's use MNIST application to get data to get sample data from. And just yeah, let's start it. So it will take us some time, like we see, like 5-8 minutes to run through this pipeline. But while it's running, I'm actually kind of running out of time, but I would like to borrow some time from you guys and wait for this to be finished. And in the meantime, I'm happy to take questions. So feel free to post questions here. Just opening this question board. In case of any questions has been voiced out like separately by, I believe, like ODC organizers, just let me know.
I will read out some questions. There are 2 so far.
Okay.
So the first one is from Nikita Kayurov. Is it an open source project which can be integrated in our own workflow, or it is a commercial service?
Yeah, good question. So for that Hydrosphere project is kind of 90% open source, 10% closed source. We are happy to collaborate on that. So it could be integrated. Just need to talk separately about the limitations of open source project that we have. So we tend to make it production ready, no hidden bugs there, but there is some functionality we cannot open source. So especially which is kind of industry specific, because for this monitoring piece, yeah, it's a use case specific. You cannot have a silver bullet monitoring model that will be used for any sort of use cases to identify some data drift in images, identify data drifts in text data into tabular data. So this stuff is closed source. All the tooling for deployment is closed source. Kubeflow integration is obviously open source, and all this the content for this webinar is also open sourced on GitHub.
Thanks. The next question is it only support Google Cloud? Any Amazon Web Services cloud adoption plans?
Good question. So Kubeflow community supports all the clouds formally, but in reality, there are some bugs there just because of early stage of this project. But yeah, Kubeflow itself could be run on any cloud whenever you have a stable Kubernetes cluster. Hydrosphere is cloud agnostic. We can run on any cloud. Basically, in this setup, the Kubeflow runs on Google Cloud, but Hydrosphere UI runs on AWS Cloud. So just a multi-cloud deployment in this case. Good question. Yeah. In the meantime, I forgot to show you the MLFlow integration. So the same experiments are being, if you remember, the same experiments are being logged into MLFlow, and you see here there is a nice way to filter experiments by particular parameters, metrics. For instance, give me the experiments with the accuracy above the threshold, and so on and so forth. So you can compare different runs just side by side. This aspects of pretty simple UI, but in order to do the same in Kubeflow, it's kind of more pipeline centric rather than experiments tracking centric. You do have all that metadata as well. For instance, each run has an output. Yeah, you see here it has an output. You can explore it, but there is just from the user experience perspective, there is no a similar kind of spreadsheet-like interface to compare runs and just go through the runs and see those. There is some kind of, when you go through that run, you can adjust this, amend this table with metadata from the training pipeline or from other metadata you would like to put here, but still it's kind of lagging some functionality of like searching. For instance, you can search just by name, not by like model accuracy, for instance. So it's just a simple, very simple UX issues, nothing fundamental. I believe like Kubeflow will add this functionality in the next like releases. However, for now, in most of the setups, we use both Kubeflow and MLFlow just for different purposes. They do not kind of do not dictate one tool versus another. Yeah, let's see what's going on with our rerun. Okay, so there is something, yeah. The testing is in progress, I guess. So the model is there. So it takes, yeah, just to explain, there are sometimes it takes some time to launch the Docker container. That's why the module testing might be kind of failed. That's why there are some requests like retries here, and usually it takes like 1 to 2, 3 retries to wait for the model container to be launched. So nothing crucial.
Maybe meanwhile we can go through some more questions.
Sure, yeah.
So there is another question from Dmitry as well. Could you please show the deployment and serving source code for Hydrosphere?
Wonderful. So switching to this source code for deploy, let's start with release the model. Basically, there is a Python SDK. When you just describe the metadata you would like to pass, here is a signature. It's explicitly specified, but like in most of the cases, especially with TensorFlow, if you save the model in saved format, we extract it automatically. You specify some configs for monitoring. So basically, what exactly you would like this model to monitor, us to monitor for this model, and you assemble this object and basically send it to the Hydrosphere. We package it like SDK with a CLI in the background. It packages the model binaries, packages all that information. Also, if we have a path to the training data set, we profile this training data set, gather some statistics from that. For instance, some distributions, basically capture all like more than 100 different just classical statistics from that training data set in order to monitor later a training serving data skew. And the DSL is like this. So there is also a Python, just a CLI. So you can use it just from the console or from Jupyter Notebook if you want to play with that. Yep. Let's see what's there. Yeah, so the model is there, so it's released. Let's take a look at the monitoring piece. I believe the production traffic still goes there. So we just swapped. We swap endpoints. Let me just go to, yeah, 1 second. Yeah, so accuracy, so it's a version 17th. let me, where's the accuracy here? Yeah, if we compare with version 16 and click like 2 hours here. So by some reason accuracy, but it is supposed to get displayed like recovering accuracy. By some reason it's not available. Something is not perfect on a demo, but for this like drift detector, you see, and we compare with the previous version of this model. So before that, let me enlarge it for you guys to see it. So we had some like it's not enlarging in the right way. So we had some like letters in production, and we observed kind of red flags. Then we retrained the model, uploaded a new version, and now we see that kind of it's not. It became better, and it recognizes letters then. So for the purpose of this demo, of course, we had a trick of providing ground truth labels for this retraining on this retraining process. So in production, you may have like a different process of providing the ground truth labels. But however, just in order to show that mechanics and these cycles, that could be, I believe this is like illustrative for you guys. So in terms of the demo, this is what I wanted to show you guys. Well, let me switch to the final screen just for your records as the next steps. Just go and try. The references are here. Ask questions. You can contact me directly or just info@hydrosphere.io. There is a GitHub channel on Hydros serving repository. This is kind of the main like root repository for those serving components. And please use this like QR code to. I believe there is some like calendar availability is being integrated with this QR code, so you can easily just book the meeting right away. So that's it from my side. Where we ran out of time. However, I believe we can take we can take some more questions.
Yeah, there actually are some questions more. How Provectus is related to Hydrosphere or Kubeflow?
So Provectus is a consulting company that delivers AI solutions to enterprises, and we are one of the Provectus is one of the top AWS consulting companies in in machine learning and DevOps space. And that project has emerged as a tool set that we've built for ourselves. So, for instance, to deliver something to production to our clients, we had some tooling, and we faced those issues. So currently, like Hydrosphere is Provectus provides a consulting like capabilities for Hydrosphere, but Hydrosphere is a purely product initiative and product business. When we open source product business, when we kind of have an open source version, we have a Red Hat model. We do not sell license. We basically sell managed services and support for this product. So I believe it's not going to be a product and company pitch. If you want to know more details, don't hesitate to contact me directly.
Thanks. Another question is, I'm not sure I got how you deal with data draft and removing the out of context data. Is that done manually, or can the tool identify and remove it for you?
So good question. So there are no magic there. So we can there are some kind of baseline methods that is built into our product for drift detection. So some kind of unsupervised methods when we basically profile input, build that check that distribution, compare the distributions with the training data set, and also compare these distributions with in a time dimension, so over time. There are also some like model specific drift detectors that we've built, for instance, for text, for image, for our other use cases. Those are basically, we use machine learning to monitor machine learning. That's a short short answer. I believe for like deeper explanation how it works and the specific, especially for different use cases, we need like another 1 hour. I probably will probably think about like having another one webinar on this topic. But however, if you have like, if you're interested, we can talk offline about this. And if you for removing that edge cases, filtering out, of course, also there's no any magic there. You basically need to, if you see some outliers, it's very use case the specific. Either you want to filter them out, just you basically you kind of adjust your machine learning pipeline manually to filter them out. Or you can incorporate it into your training, retraining pipeline. So your model will be trained on those samples. If it's not the outliers, if it's just a real and new cluster of data has been discovered, or you need to have some logic behind this, incorporate some logic in your model to handle those drifted samples.
Okay, thank you a lot. It seems that's it with the questions. Thank you for the presentation, Stepan. It was a pleasure.
Thank you, everybody.